Welcome to our Advanced Mathematical Theorems quiz breakdown. Today we'll explore some of the most celebrated theorems in mathematics, each with its own unique beauty and application. From the elegant geometry of triangles and quadrilaterals to the powerful properties of numbers and functions, these theorems form the backbone of mathematical reasoning. We'll start by looking at Seve's theorem, which connects the concurrency of Sevians in a triangle to a simple product of ratios. Then we'll move to Ptolemy's theorem, a classic result about cyclic quadrilaterals. As we journey through these concepts, you'll see how each theorem not only solves specific problems but also reveals deeper patterns in mathematics. Let's dive in and see how these theorems work in action. Let's take a closer look at some geometric theorems. Seve's theorem tells us that for a triangle ABC, if Sevians AD, BE, and CF are concurrent, then the product BDDC times CEA times AFFB equals 1. This powerful result helps us understand the balance and symmetry within triangles. Moving on, Ptolemy's theorem gives us a relationship in cyclic quadrilaterals. The product of the diagonals equals the sum of the products of opposite sides, or F equals AC plus B. These theorems are not just abstract ideas, they're tools that help us solve real geometric problems, from calculating unknown lengths to proving concurrency and collinearity. Their elegance lies in their simplicity and the way they connect different parts of a figure. Now let's shift our focus to theorems involving numbers and functions. Fermat's little theorem is a cornerstone of number theory, stating that if P is a prime and A is not divisible by P, then a P1 is congruent to 1 modulo P. This result is fundamental in cryptography and modular arithmetic. Mean value theorem bridges calculus and real-world change, guaranteeing that for any continuous and differentiable function on A, B, there's a point where the instantaneous rate of change matches the average rate. And in complex numbers, De Moivre's theorem elegantly connects trigonometry and exponentiation, showing that cos plus I sin xn equals cos nx plus I sin nx. These theorems highlight the unity of mathematics, linking geometry, algebra, and analysis in surprising ways. Geometry also gives us practical tools for measurement and understanding structure. Hicks' theorem provides a neat formula for the area of lattice polygons. Area equals I plus B21, where I is the count of interior lattice points and B is the number on the boundary. Heron's formula lets us compute the area of any triangle from its side lengths, a vital tool in both pure and applied mathematics. Stewart's theorem relates the sides of a triangle to the length of a Sevian, deepening our understanding of triangle geometry. Finally, the Euler line in triangles passes through several important centers, but notably the incenter usually does not lie on this line. These results show how formulas and lines can reveal hidden order in seemingly complex figures. As we wrap up, notice how each theorem we've discussed is more than just a formula. It's a bridge connecting different areas of mathematics. The law of cosines generalizes the Pythagorean theorem, showing how trigonometry extends geometry. Stewart's and Seve's theorems reveal deep relationships within triangles, while De Moivre's theorem links algebra and trigonometry through complex numbers. These connections are what make mathematics so rich and rewarding. By mastering these theorems, you not only solve challenging problems but also gain insight into the underlying unity of mathematical thought. Keep exploring, and you'll find that every theorem opens the door to new discoveries and a deeper appreciation for the beauty of math.